Hello and welcome to today's video lesson on the effect of temperature on K. So this is a continuation of Le Chatelier's principle. So let's look at our exothermic example, which is A plus B produces C plus energy. So remember that when we have energy on the product side, it's exothermic, meaning that heat is being lost to the surroundings. Also, in this chemical equation, I just made up a generic example using the letters A, B, and C, but the K equilibrium constant, that always equals the concentration of products raised to their mole ratio divided by the concentration of reactants raised to their mole ratio. So in this case, the K constant for this equation is K equals the concentration of C, that's my product, divided by the concentration of A times B. Okay, so let's look at question A. What happens if we increase the temperature? So temperature, when we increase, it'll actually increase the entire reaction, but because energy is on the product side, my energy term, this will go up. Okay, so I'm going to mark it on my equation, energy will increase. Because energy increases and it's on the product side, it's going to absorb or combine with C. So C is going to, if we look at the equation, C plus energy, that will give me reactants. So that will actually cause my equilibrium to shift this way to the left, forming more of A and more of B. So in other words, what happens if we increase the temperature? The equilibrium shifts or moves left, okay, towards the reactants. Now, the other thing is temperature is actually a variable that can also influence the magnitude of K. So it will change also the value of my equilibrium constant. So let's look at our equation over here. If K equals C divided by A times B, because my equilibrium is moving to the left, that means my denominator is going to increase. So A will increase and B will also increase. Now my product C over here, it's getting consumed by the energy. Remember how we increased the temperature, right? So because this is getting consumed and combined with the energy, C's concentration will actually decrease. So that means I'm going to have a smaller numerator and a larger denominator in this example. So not only will my equilibrium shift left, my K constant is also going to decrease. It will become a smaller number because the ratio of product to reactant has now changed. So let's try the flip side example. So let's continue with our exothermic example over here. So in my exothermic example, instead of increasing the temperature, we're going to decrease the temperature this time. So let's mark it down on our equation. Energy term, will be decreased. So what is going to happen if we decrease the energy? Well, C, the product, it doesn't have as much heat to react with, so my equilibrium is actually going to shift to the right this time. A and B are going to have a greater chance of collision and greater chance of reacting to form C. Plus, according to Le Chatelier's principle, if we take something away, the system will want to replace that. So if we decrease the temperature, my equilibrium moves to the right towards product. Now, what is that going to do to the K constant? So remember, temperature will also change your magnitude of K. So if A and B are colliding and moving to the right, that means this product will increase, C will go up. And that also means A and B, these are going to go down as concentrations. So if I go to my equilibrium constant, my numerator or my product C, that will increase. My denominator, that's the reactants A and B, those will decrease. So I'm going to have a larger numerator and a smaller denominator, which means my K constant will increase. Okay, that's how we tackle a problem like this for Le Chatelier's principle and looking at how heat or temperature changes change your equilibrium constant. So let's try an endothermic example. So this is like the same thing. I just flipped the equation. So endothermic, C plus energy gives me A plus B. What happens if we increase the temperature? So let's take our energy term, let's increase that, and we can see that from this example, the reactant C, it's going to have a lot more energy to absorb in this endothermic situation. That's going to cause my reaction to move to the right. So I'm going to have an increase of A, an increase of B. C will decrease because it is getting consumed in this reaction. So we're going to say here my equilibrium shifts to the right, or the products. Now, what will this do to the K constant? So we have to look at this K expression. Because of how I wrote the equation, remember the equilibrium constant is products, concentration of products, divided by concentration of reactants. Because I flipped the equation, I need to adjust my K constant. So again, because my equilibrium moved to the right, my numerator is increasing. I've got lots of A and B. The denominator, that's my reactant, this is decreasing. So there's not as much C as the shift occurs. So I'm going to have a larger numerator, a smaller denominator. The K constant in this case will increase. Okay, and then you can try the other example, the endothermic one, by decreasing the energy and seeing what happens. So let's try a challenge. So in this challenge question, I have the same chemical equation, but it's at two different temperatures. So at 100 degrees, the K constant is 0.17. At 200 degrees Celsius, the K constant is lower. It's 0.091. Is this reaction endothermic or exothermic? So let's look at all of the things we just learned. If I scroll back, K will decrease when we increase the temperature for an exothermic reaction. And that's what this situation is showing me. So this is going to be an exothermic reaction because K is going to decrease when temperature increases. Let me know if you have any questions about this concept, and thank you so much for tuning in.